Mike is a wireless security researcher who makes hardware for hackers. And he founded Great Scott Gadgets in an effort to put exciting new tools in the hands of innovative people. And one of these tools that we'll talk about now is HackRF, a low-cost radio platform. All right.
Thank you, Dan. How's that? All right, thanks everybody for being here. I've given this talk the same title that I've given other talks, but screw that. Let's do something a little bit different. HackRF, just very briefly, how many of you guys have heard of HackRF? Awesome. How many of you saw HackRF on Kickstarter? How many of you backed HackRF on Kickstarter? Wow, thank you so much. Really, I truly appreciate it. It was a pretty amazing project. Software-defined radio, for those of you who are new to it, is just a very simple concept of digitizing radio waveforms from an antenna or spitting out waveforms from that were digital, turning them into analog and spitting them out on an antenna to transmit. So you can transmit or receive using the same type of technology that we're accustomed to with PC sound cards, for example. We're used to dealing with digitized sound waveforms. SDR, software-defined radio, is just doing the same thing except we're digitizing radio waveforms instead of sound waveforms, which gives us the capability to produce or analyze arbitrary radio waveforms, where in the past we had to have special hardware for a particular type of modulation on a particular frequency. Today, with today's SDR technology like HackRF, we can have basically a universal radio where we can interact with any kind of modulation on a wide variety of frequencies. So HackRF, it was kind of an ambitious project from the start. I wanted the thing to run from 100 megahertz to 6 gigahertz, which is a very wide operating frequency range. We ended up exceeding that range. I wanted to be able to transmit and receive. I wanted to have all this in a portable platform that's bus powered, so I don't have to carry around a wall wart or anything like that. And I wanted the whole thing to be open source software and open source hardware. And I went to DARPA and I said, hey, I want to do this whole thing, and I want it to be completely open source, and I want anybody to be able to build it, and I don't want any restrictions on my ability to talk about it or publish any information about this project, and I want to build 500 of these and just give them away to people to beta test, and I want you to pay for it. And they said yes. So thanks Mudge, thanks DARPA, thanks BITS. Everybody has been fantastic in support of this project. And Cyber Fast Track for HackRF was a big win. This was something that I wanted to do for a long time and never had the time or money to get it done, and CFT made it possible for me to take this dream and make it a reality. So this is a picture of HackRF Jawbreaker, which is the beta platform. How many of you have a HackRF Jawbreaker? A few, excellent. I've talked a lot in the past about how we got here, what HackRF is and why we're doing it and how we did it and how we got to this point where we produced Jawbreaker, and we have this open source hardware design that's functional, that is a general purpose SDR platform that anybody can build and anybody can use. But today I want to talk about the present and the future of the project. So right now, these circuit boards are being manufactured. So I don't have one to show you today because hopefully there will be some bare circuit boards delivered to my house before I get home tomorrow. It's a brand new design called HackRF One, and it's very similar to Jawbreaker. It's a little bit different size and shape. It's a little smaller. It's about 14 square inches compared to almost 17 square inches for Jawbreaker. It doesn't have the same PCB antenna on it that Jawbreaker had, which was probably a mistake in the first place. And I just want to point out a few things about it. In the lower left-hand corner, you can kind of see there's a big rectangle. That's a big dotted line around there. That's an area where an RF shield can be installed, can be soldered over that section. So the whole RF section can be protected to keep it from being influenced by outside signals, maybe from other parts of the board, for example. On the left-hand side and the lower left-hand side, there's kind of those three horizontal bars. That's where the SMA connector will be soldered on to the edge. So the connector will be sticking out the edge of the board instead of coming out vertically from the board like it is on Jawbreaker, which you can see back here. You can see in the bottom there's that SMA connector sticking up. So now the SMA connector will stick out to the left. Now on the other side of the board, on the right-hand side, you can see two other SMA connectors, and those are for clock reference input and clock reference output. And this is a really exciting development that wasn't even a primary goal of the project, and we didn't even have tested by the time we finished the Cyber Fast Track project. But all along, we wanted to have clock reference input and output actually working on this thing, which gives us the capability to have like multiple HackRFs synchronized to a single clock, or have one HackRF drive the clock of another. So you can just get two HackRFs and connect a cable between their clock, one's clock input and the other's clock output, and they'll be synchronized, which opens the door to a whole bunch of interesting experimentation in multiple antenna technologies, like phased array antennas, synchronized clocks for transmit and receive, which would be very important if you wanted to do something like a cellular base station type of application. If you wanted to capture more bandwidth than the 20 megahertz that HackRF supports, you could actually do multiple HackRFs and kind of add their bandwidth together, and it will coherently add together because their clocks are synchronized, and you can do all kinds of interesting things. So that's a really nice feature that we actually tested and got working, and is going to be on HackRF One. Then on the right-hand side also, there's the USB connector, that kind of funny-looking thing on the edge up in the upper right that looks sort of like one of the Transformer logos. It's like Autobots or something like that. And then on the left-hand side, there's a bunch of LEDs and a couple of buttons. So there are two buttons that stick out the left-hand side and the upper left that allow you to reset the device or put it into a bootloader mode. So it's just a little bit easier to develop firmware for the thing and hack on the thing. All in all the rest of the stuff, it's kind of a tricky layout, but it's all stuff, all components that were in Jawbreaker, and they're mostly connected together in the same ways, so you can do the same things on HackRF One that you could on Jawbreaker. There's also a bunch of these pin headers on the right-hand side, kind of surrounding the big chip. And those pin headers there are more pins, and they're kind of consolidated into fewer, larger headers, which makes it just a little bit easier to build expansion boards that can fit on top of the thing. And I'll talk a little bit about one particular expansion board. But I want to make it very hackable. I want people to be able to design their own expansion boards for this thing. As an open source project, as an open source developer, I think it's very important to try to make my projects as hackable as possible. So I want to show you a little bit. Earlier today, I just kind of did a YouTube search and just checked out all the different things that people are doing with HackRF that they've actually published. So I found some things that I hadn't even seen before today. So this was one, somebody posted a video of, you might notice in the middle, like 94, 95 megahertz. Each of these peaks in here is an FM broadcast station. So this is somebody who's just using HackRF to listen to FM radio. Now this is kind of ridiculous overkill, right? To have to have this 20 megahertz bandwidth, you know, like $300 platform. Wow, that's my FM radio. But the cool thing is, if you look back up on the screen, oh, he's going to show the pan to the antenna. I'm going back to the screen. Each of those is an FM radio station. The cool thing about this application with HackRF is that you can receive all the FM radio stations simultaneously, not just one. And I've actually done demos where I've like listened to 3 at a time, and you can just like tune around and pick which ones you want. And I've tried doing more than 3, but 3 is hard to listen to. Like 1 is easy, 2 is hard, 3 is just like, you can kind of pick out little bits and pieces of. Anyway, it's a silly demo. But here's another demo from that somebody else posted where they're actually transmitting FM radio. And I saw another one that I don't think I managed to capture, where somebody was transmitting. So this is somebody like using GNU Radio Companion. They have this whole flow graph that they're showing here, and then they're going to transmit it over the HackRF and pick it up with I think like their clock radio or something. So it just like you might have a little FM broadcast, like a personal FM transmitter that might you use in a car, for example. Same kind of thing. And I've also seen this done on the HackRF with DRM, the digital radio protocol, I think it was, or maybe it was DAB. I don't remember. But I saw somebody do a digital broadcast, radio broadcast of audio using a HackRF. So this kind of illustrates that HackRF is used not just for receiving, but also for transmitting. Now this is somebody who is picking up signals from a 2.4 gigahertz wireless keyboard and mouse. And there are a lot of 2.4 gigahertz input devices on the market. Some of them are Bluetooth, but Bluetooth really was unpopular for those types of devices until fairly recently. It's only with the popularity of tablets that Bluetooth has kind of become more popular for keyboards. But until that point, almost any wireless keyboard or mouse you would buy would be a 2.4 gigahertz proprietary protocol. And this is an example of somebody picking up some signals from one of those proprietary protocols. I don't know how much or if any work this person has done on actually decoding those signals, but they're definitely being detected. And this software that's being used is SDR Sharp, which is running on Windows. So I personally do everything in Linux, and I develop in GNU Radio. But this person was using SDR Sharp, which also has HackRF support. This is something that I was playing with not too long ago, which was a Lego remote control car. So I was able to capture signals at 27 megahertz from the car and analyze what signals made it do what, and actually like replay and make the car move by transmitting signals from my HackRF. So hopefully by now you're starting to get the idea here that this is a truly universal radio, like 2.4 gigahertz, 27 megahertz, simple amplitude shift keying or on-off keying, like this car is using, to more complex modulations. This is a capture this is actually a spectrogram that shows frequency shift keying of a car remote keyless entry system. So this is a capture. A lot of those use amplitude or on-off keying, but this one actually uses frequency shift keying. This was captured by Dragorn, and he started to analyze it a little bit. So you can like capture and replay these things regardless of what frequency they're on, regardless of what modulation they're on, and analyze them in software. Now this is something that I think is especially cool. This is the PortaPack, the HackRF PortaPack, which is a little board that Jared Boone made. You might not be able to see it, but this is a board that's stuck onto a jawbreaker. So this is actually an expansion board on a HackRF. And he's running entirely on the HackRF CPU. So there's no attached host computer doing anything here. Oh, there, you can see the jawbreaker that he's connected to, right? So the only thing that's connected to, he has a debugger connected, but the only thing he's using that USB cable for right now is power. So he's running this wideband spectrum analysis on the jawbreaker itself and displaying, I'm going to pause this because the video is getting ahead of me, and displaying it in real time on a little LCD panel. And so he can run around, pop a USB battery pack on that thing and run around and do real-time spectrum analysis across, and visualize 20 megahertz of bandwidth and anywhere between 10 megahertz and 6 gigahertz, which is pretty amazing. And I think he said he was running something like 1,000 FFTs per second on the little arm on the HackRF, which just blew me away. I don't know how he's doing that. But then he kicked it up a notch and put this 2-foot wide vacuum fluorescent display attached to his HackRF. So this was at Maker Faire, and he put this big wheel. That big round thing has a quadrature encoder on it, so you can like spin the wheel, and it'll change the frequency of the spectrum analyzer. And so the same exact thing that he was doing in a handheld platform, then he was doing with this big display at Maker Faire, and again, doing all the CPU, all the processing on the ARM that was on the HackRF itself. This is something that I just found today that I hadn't seen before, and I'm not entirely sure what's going on here. But apparently, this Android phone is decoding Morse code that was being picked up here on the HackRF with this host computer, and this is apparently some broadcast signal in Budapest, and somehow he's then giving like this demodulated or partially demodulated signal over to the Android application that knows how to decode Morse code in real time. Yeah, neat. I don't totally know what's going on, but it's neat. Here's somebody who was just like, when he got his HackRF Jawbreaker, he just like, let's see if I can get 20 megahertz of bandwidth, and sure enough he did, and here he's capturing a whole bunch of different GSM channels simultaneously. And you can see them mostly, especially over on the right-hand side, you can see some things that in the waterfall that are kind of changing in the time domain. And those are active GSM channels that are switching on and off, or switching back and forth between one device or the other. It's a time division multiplexing thing. Not only can you receive GSM, but you could receive a whole bunch of channels of GSM all at once, and that's what he's showing here, which is pretty neat. And this is a screenshot from somebody who is showing how to actually decode those GSM signals that might be captured with a HackRF. These, I think, were captured with a HackRF, and actually like decoding them and dumping them into Wireshark and so forth. Now, actually decrypting them is another challenge, and that is possible, and the tools to do it are becoming easier to use, but it's still challenging. And this is somebody who was decoding some POXAG pager traffic. And you see they've actually obfuscated some of the text there, because if you do sniff any pager traffic, you'll quickly see things that you know shouldn't be published. Because they're very popular, for example, in emergency services and hospitals. Oh, and in fact, I see the word hospital right there on the screen. So you can decode a whole bunch of pager signals all at the same time, like a whole bunch of different channels all at once if you want. And you could also transmit pager signals. Dragorn sent me a pager. I don't have it with me, but he sent me a pager so I could do demos with it. I plug in a HackRF to my laptop, and I have my pager, and I just send pages to it. Right? Really simple, but fun. And this is something that was just published the other day by Luke Barrett, who's doing some interesting stuff with the Washington, D.C. municipal public safety radio systems. And he's implemented mostly by like taking chunks of code that other people have done, but he's put them all together into this really nice system that allows him to analyze in real time the trunking radio network used by public safety in Washington, D.C., where each of the channels is using a P25 modulation, but I think this might be a proprietary trunk channel, I'm not sure. But anyway, he's doing real-time monitoring that tells him information about like who's using what channel, and then he can go to any one channel and decode it, and he actually has it up on the web. If you go to openmegahertz. Oh no, I forget, is it .com, .org, something, Open Megahertz. He's actually put this up where you can listen in real time. It's like a scanner for listening to all of the channels of public safety radio systems in Washington, D.C. And this is using a HackRF, and it's receiving all those channels simultaneously. This is something that is interesting. AIAS is a system for transponders or beacons on boats. So boats are transmitting information about themselves all the time, and this is somebody who's used a HackRF to receive those signals and map them and show where boats are in his vicinity. This is a little screenshot from GRPhosphor, which is a brand new GPU accelerated visualization tool for spectrum analysis using GNU Radio, and it gives a really nice display that's similar to, if you're familiar with high-end spectrum analyzers, like real-time spectrum analyzer, that type of display. And this is a signal. This is an image produced from a signal captured from a weather satellite. This was captured with HackRF. So every single screenshot I've shown you here, every single little video, is something that somebody has done with HackRF, like within the last 3 months. And so I wanted to just kind of give you a flavor of what's going on with the project and what some of the capabilities are. And hopefully some of you have some interesting ideas for what else you might want to do, because kind of the sky's the limit. You can transmit or receive virtually any radio signal that you can imagine. So with that, I think I'd like to just say thanks and open it up for questions. Anyone? Yes? The range. That's a frequently asked question that has no good answer. The transmit power, it varies depending on frequency. But at a maximum, it's going to be around 10 milliwatts. And at a minimum for most frequencies, or the maximum at some other frequencies is going to be around maybe 1 to 10 milliwatts, something like that for most of the frequency range. That's not very much transmit power, but it's sufficient to do across the table, across the room, experiments, anything in this room I should be able to pick up with my HackRF. But, or I'm sorry, I'm talking about transmit. I should be able to transmit something to something in this room, right? I can open my garage door from tens of meters away. But it's not anything that's going to be power that's going to go more than tens of meters. So if you want to operate over longer distances, you need to investigate transmit amplifiers. And if you are going to amplify, you need to filter. And if you're going to amplify, you need to know your laws. So you're unlikely to get into trouble doing stuff at the low power that the HackRF provides on its own. Other questions? Much? Okay, so Mudge is calling out other competitors who are maybe releasing products at lower price points than they originally intended because of HackRF. If that's the case, then I'd say that HackRF accomplished its goal. It's not the only goal for HackRF, but if those products had been available at that price point before the HackRF project, I might not have ever been motivated to do the HackRF project, right? The reason I wanted to do HackRF was to make this technology more accessible to more people, and especially people within the information security community. If you have to spend a couple $1,000s to get a hardware platform to do this kind of stuff, not very many people are going to do it. But getting it down into the $300 price range starts to get more interesting, I think, and make the technology more available to more people, and I think that's a good thing. So even if HackRF is a complete commercial failure, if its only impact on the market is reducing the prices and increasing competition, then I think it's a net win for everybody. And then, of course, the other big motivator for HackRF was to get an open source design out there, because none of those other products are open source hardware. You don't have you do have the ability and the right to produce your own HackRF, download my design files, get it manufactured, and even sell it if you want. Might not be the most neighborly thing, but it would be totally legal, and I very much support that. So any last questions? One more.
For people with a background in reversing software, hacking software, and who haven't really gotten into radio yet, what are the skills they need to build up to do that, and how should they get those skills?
Okay, this isn't a plant, I promise. But I am on the verge of starting to publish a video series that is an adaptation of my training class that I do frequently at HackerCons. That is a 2-day, very intense class that teaches people who have a background in software but no background in radio or digital signal processing. It teaches those kinds of people with those kinds of backgrounds the basics you need to know about digital signal processing and radio and SDR so that you can start experimenting with stuff like this. And in particular get into digital stuff. So like there are oodles of like proprietary digital wireless technologies out there. And we encounter them all the time, but being able to hack on them is something that you need some skill, some knowledge to be able to do, and that's what I try to do with my 2-day class. So I'm in the process of turning that into a video series, and I'm working on my first episode now. It's going to take a while to roll out the whole series, but I'm starting now, and I'll get a few episodes up within the next couple of months, and we'll keep going with it until I get it done, and maybe even go a little further than I've been able to do in my 2-day class. But the short answer of like what homework you should do on your own is, number one, digital signal processing. You may know software, but that doesn't mean you know digital signal processing. And there's a lot to that field. And that's the number one thing that I think is difficult to understand and takes a lot of effort to learn. Like, it doesn't take that much effort to learn real basics about radio propagation and antennas and how the RF works. You don't need to know that much about it. I mean, yeah, it is a deep field, but you don't need to know that much about it to do practical things. But you do need to know a lot about DSP to do practical things. And that's what I focus on mostly in my course. So thank you, everybody. Is there, Dan, are we doing the panel here or elsewhere? Or? Okay. All right, thanks.